Instant Insanity is a puzzle that's been around since about the 1960s. It was introduced by Parker Brothers back then, but was in existence in the 1940s under the name of Great Tantalizer and Katzenjammer in 1900, so it's been around for quite some time. As you can see in its box here, it consists of 4 cubes. The cubes have different colors on the faces, the sides that is of the cube. It turns out that when you look at one cube and another cube, they're not colored the same way. We'll learn how to solve this using a mathematical idea known as a graph. I'll make copies of these virtually. So these are the same 4 cubes. The idea is to stack the 4 cubes so that as you look around the stack, you get one color on each side, or one of each color on each side. Let's take the 4th cube. It's got a blue on the left, a green on the right, and we'll just place it on the bottom. The 3rd cube has a green on the right already, so it can't go directly on top of the 4th cube, but if we rotate it so that the green is on top, we'll end up on left, or white on the left and the right. The 2nd cube has a blue on the left, and we already have that, but it has a red on the right. If we flip that cube over so that the red is on the left and the blue is on the right, and stack it, we'll be okay. The white face that was on top turns to the bottom, and a green face actually appears that was on the bottom, hidden by the other faces. Look at the stack as we have it. Think about what colors we need on each side. Does the 1st cube have what we need? Well, of course. The left side needs a green, the right side needs a red. We have green and red, but they're on the wrong sides. If we flip it over, we'll end up with a green on the left and a red on the right. Is this actually a solution? Well, it will be a solution if the faces that are hidden also have the property that we have one of each color. Let's pull them away from the back just to see. Ooh, it doesn't look good. Look at that. When we pull it away, there are no greens whatsoever, and the left one doesn't even have any white ones. In order to solve the puzzle, we need to think about the structure of a cube. Here's a cube. You have a blue, a red, and a white face showing. Let's suppose we put the blue one on the left as it is. Are we guaranteed that the red will be on the top and the white on the right? Of course not, because if we rotate it by 90 degrees so that the red comes down to the front right, we see what was hidden in the back, the green one. There's a 4th side that we don't know as well, and so the blue actually is adjacent to or next to 4 different faces. So looking at the blue compared to the other 4 that are next to it, we don't know exactly how the cube will be. We're looking for something that's known as an invariant, something that no matter how the cube is arranged will still have that same property. Well, as I said, we have a blue face. There are 4 faces adjacent to it. Each cube has 6 faces total, so there's another face that we haven't discussed, and that's the one that's opposite the blue. That's actually the one that we'll focus on because no matter how you orient a cube, when you have 2 faces that are opposite each other, they'll remain opposite as we revolve it around. I've drawn the cubes again, this time blowing out the sides so that we can see the relationship between sides and the opposite faces. We'll keep track of which sides are opposite which. I've got a white opposite green on the back left and front right, a red on the front left, a blue on the back right, and a white on the top and a blue on the bottom. Similarly, we have red opposite red, blue opposite red, and white opposite green on the 2nd one. On the 3rd one, we have red opposite green, white opposite blue, and white opposite red. And on the 4th one, we have red opposite green, blue opposite blue, and white opposite green. We've taken these concrete things that we can hold, the cubes, and we've made them a bit more abstract by establishing this relationship. So we can get rid of the cubes. Well, maybe we can and maybe we can't. For our purposes, it turns out we can. However, if you ask the question, given a pairing of the 3 pairs of opposite faces, can you recreate the cube exactly? The answer is no. But for our purposes, it's okay that there is some ambiguity. We'll discuss that at the end if you want to stick around after our 2nd puzzle that we solve. The idea of faces being opposite is a symmetric relation. What we mean by that is if one color is opposite another, then the second is opposite the first in the same respect. On the first cube, white is opposite green, and green is opposite white. red is opposite blue, or we could have said blue is opposite red. It doesn't matter. When we have this type of symmetry, we can represent the relationship in a graph. We'll make a vertex for each color, red, white, blue, and green. And then whenever there is a pair of opposite faces that have two colors, we'll draw an edge between them. So you'll see on the right side we have white opposite green, and so we color the white to green edge. We have red opposite blue, so the left side we have red to blue, and then white opposite blue, we have a little diagonal there. For the second cube, we have a little bit of special relationship. There's a pair of opposite faces that are the same color, which will form a loop on the red. The blue opposite red, white opposite green. And then we do the same thing for the third and the fourth, getting another loop because we have a blue opposite blue in the fourth graph. Once again, we have a different abstraction of the cubes, these four graphs. But notice that the four graphs share the same vertices, right? Red, white, green, and blue. We could put them all on one graph with some caution. If we put them all on one graph, we'll lose the information about which cube they came from. So as we put them on the graph, we'll also label each edge with which cube they come from. Here's the first graph with ones on the edges. Now I've bowed out the edges a bit because we'll have some repeated edges as we add more and more graphs. We'll add the second graph, which you see produces the loop on the red vertex. We add the third, we'll get an X in the middle with a line, an edge across the top. And then we get a new loop on the blue vertex and sort of a V in the fours on the right. This graph is enough to know what we need to know about this solving the puzzle. Now let's see if we can use this graph to try to solve the puzzle. We'll fail and we'll realize why we failed as we do it. I'll put a skeleton of the stacked cubes over here. Our goal is to do the front to back coloring on each cube, and then we'll worry about the left to right. So just the front to back right now. We need to pick something for the top cube, which means we need to focus on one of the edges marked 1. Let's just focus on the one that's red and blue. We are doing front to back, right? So we could either put the red on the front and the blue on the back, or the blue on the front and the red on the back. It turns out not to make any difference because if we do the blue on the front and the red on the back, we could rotate it 180 degrees so that the red appears on the front. So let's just put the red on the front. We now need to pick some way to color the 2 cube. There are 3 edges that are marked 2, but one of them actually will give us trouble. The loop on the red vertex will give us trouble because no matter how I color the front and back faces, I'll have red and red, which will produce 2 red sides on the front. So we can't use the loop. Let's just use the one from red to blue. Since I'm using the one from red to blue, I can't do red on the front and blue in the back, so I'll do blue on the front and red on the back. Now let's think about the solving of the puzzle. I've used red and blue on the front, I've used red on the blue on the back, I need white and green on the front and on the back. Let's look at their 3 edges. We'll color them purple. There they are, and now let's get rid of all the other edges so we can see them a little better. The problem here is that no matter which 3 edge we pick, we're either going to do red on one of the sides, which we can't do because we already have red in the front and back, or if you go from white to blue, we're going to have a blue somewhere, either on the front or the back. We can't solve the puzzle using the 2 edges that we've chosen already. Now, why is it that we can't solve the puzzle? Look at the orange ones. We have one edge coming into the red. We have a second edge coming to the red. One of those edges is there because we colored red on the front. The other is there because we colored red on the back. We have 2 edges in. We say that's the degree of that particular vertex is 2, only for the orange edges at this point. If we go to degree 3, we'll end up with 3 edges coming in, which means that we'll either have 2 red ones on the front or 2 red ones on the back, or worse, 3 on the front and none on the back, or vice versa. In the end, what we want is we want to have each vertex be of degree 2, 1 for the front and 1 incidence for the back. Once we've done this, we're actually going to think about which one is going to go on the front and which one is going to go on the back. Because I did red on the front and blue on the back, you can think front to back, we are going to draw an arrow from the red vertex to the blue vertex. When we move from one color to another, the first color will go on the front, the second color that we arrive at will go on the back. On the second cube, the blue was on the front and the red was on the back, so we'll draw an arrow from blue to red. This is called a directed graph. Let's review where we are at this point. Here's our graph. We're going to color front to back. To color the front and back faces, we're going to choose an edge from each cube. So we'll choose a 1 edge, a 2 edge, a 3 edge, and a 4 edge. We're going to choose them so that the degree, that is the subgraph that we get, the degree of each vertex will be exactly 2. Not less than 2 because then we don't have enough of a particular color on the front and back. Not more than 2 because then we have too much of that color. For the left and right graph, we're going to need the exact same thing, except I've already used up some of the edges, so I can't repeat the edges that I used from the first graph. So we've got to be careful in making those choices. Let's put it all together here. We started by labeling the cubes 1, 2, 3, and 4. We created a graph with one vertex for each color. Now for the long description. When we had a pair of opposite faces that were colored 2 different colors, we drew an edge between those 2 colors and labeled the edge with the cube number that we came from. If we had a pair of opposite faces that were the same color, we labeled that particular loop we created a loop on that color with that edge label. Then we found 2 subgraphs, each of which contains all 4 vertices so that the degree of each vertex is 2, and you can't use an edge more than once overall. Then we turned the edges into directed edges so that the in degree, which I'll define in a moment here, the in degree and out degree of each vertex is 1. The in degree just means how many arrows are pointing at the vertex. The out degree means how many arrows that are pointing away from the vertex. One of the graphs is going to be our front to back pairing. The other graph is our right to left pairing. When we have an edge marked a 1 or any of the other 3 numbers, when it goes from color C to color D, we'll put the color C on the front face and the color D on the back face. If we're using the left to right graph, when we go from color C to color D, the right face will be colored C, the left face will be colored D. Here we go. This is actually the most challenging part. We need to find 2 subgraphs so that the degree of each vertex is 2. Now I've done the work for you. Maybe you can puzzle it out on your own. But both of them have this little crisscross nature. We've got edges on the left and right, and then sort of an X in the middle. Match up here the edges on the purple graph with the ones within the graph. You'll see that they exist. Here is the second graph, also the same sort of shape. You've got one edge on the left, one edge on the right, different numbers though. From red to blue on the first one we have a 2, and on the second one we have a 1. We have that crisscross pattern in the middle of the second graph. We now want to add direction. Now here's the thing with adding direction. It doesn't matter which one we pick, but once we pick one of the edges within a connected component of the graph, the direction has to stay the same. So here's the direction on the first one. Let's look at the 1 edge. It goes from blue to white. Now that might be a little confusing because at the blue vertex it looks like both of those edges are coming in. But I know it's from blue to white because only one end of the edge has an arrow, and it's very clear on the 1 edge that we have an arrow pointing to the white. Well, we go from blue to white, and then we go from white to green on the 4 edge. On the edge labeled 3, we go from green to red, so the arrow up there on the red vertex is coming from the green edge, and then we move from red to blue on the 2 edge. On the second graph, we do the same sort of thing. Once you pick a direction, you know what the other arrows are going to look like because they have to follow the flow of the graph, and you have to make your way around the graph. Let's move these out of the way and show how the puzzle gets solved. I'll have 2 pieces here. One to represent as I would see it, that's the left stack, and if I remove the faces on the left and the right there, and remove the top face, the portion of the cubes that would remain is what's depicted on the right there. I'll label the sides as well. So I have the front sort of on the left there, the right also in the front, but on the right side of that. The back is on the right half there, opposite the front faces, and the left is opposite the right faces. Look at the top graph. The one edge is going to tell us what to color the top cube. It goes from blue to white, which means we're going to put a blue on the front and a white on the back. The 2 edge, remember we have to go with the direction that's already there. The 2 goes from red to blue if you follow the little X around the graph. So it goes from red to blue. So that means we have a red on the front and a blue on the back. The 3 goes from green to red. We'll have a green on the front and a red on the back. And the 4 goes from white to green, a white on the front and a green on the back. Let's look at the bottom graph. Remember, an arrow goes from the right side to the left side. The 1 arrow goes from blue to red. That's blue on the right, red on the left. The 2 arrow goes from green to white. Green on the right, white on the left. The 3 arrow goes from white to blue, white on the right, blue on the left. And the 4 arrow goes from red to green, red on the left, red on the right, green on the left. Again, it's a little confusing there because where I say right and left on the top of these stacks, the right side is actually to the left of the left visually, but that's okay. That's a nice little puzzle solution using graph theory. Let's look at another set of cubes. I'm going to number the cubes here. The top one is 1, the second one in the top row is number 2, the first one in the bottom row is 3, and then 4. We start by drawing our vertices, and then we draw the edges in and label them according to the cube they come from. The first cube has red opposite red, red opposite green, and red opposite blue. That's what we've connected here and labeled 1. The second one has white opposite red, blue opposite green, and white opposite blue. The third one has blue opposite white, red opposite white, and red opposite green. So we add those edges and label them 3s. And the last one has white opposite blue, white opposite blue, green opposite blue, and green opposite green. So we have a loop on the green vertex there. We now need to find 2 subgraphs so that the degree of each vertex is 2. In the previous one, we saw sort of an X shape in the middle with edges on the left and the right, sort of vertically. This is going to look a little bit different. Turns out that we can have a little triangle up in the top left-hand corner and a loop down from the green to itself. The other graph that we'll use will look like this. It's got that little X shape in the middle, and then a 2 across the top and a 4 across the bottom. Notice that we haven't used the same edge twice. We now want to add direction. Again, with that little triangle between the red, blue, and white, you can do any direction, but once you choose it for one edge, that direction has to match with the other edges. I chose to do it clockwise, I guess you would say. For the second one, that's the direction I choose. And now we fill in the colors. Here is our blank slate, front, right, left, and back labeled. On the top graph, this is our front to back graph. The top cube, the 1 cube, goes from blue to red. So blue is on the front, red is on the back. The second cube goes from white to blue, white on the front, blue on the back. The third edge, the edge 3, goes from red to white, so red on the front, right on the back. And the green, the 4 edge is on the green, it's a loop, so green to green. Front and back are both green. The other one again tells us the right to left relationship. The 1 edge goes from green to red, so green on the right, red on the left. The 2 edge goes from red to white, red on the right, white on the left. The 3 edge goes from white to blue, white on the right, blue on the left. And the 4 edge goes from blue to green, blue on the right, green on the left. Now I'll tell you, if you go back a little bit, you can look at that graph and you can actually find another solution. I think there might be 3 solutions total for this particular puzzle. So this one's a little bit easier than the first one. The first one, it turns out, has one and only one solution. We've done our little explanation of solving instantaneous insanity. It's a nice application of using graph theory to solve a puzzle. I mentioned a little bonus material, if you will. If you want, you can stick around for the rest of this. We're going to talk about how a particular graph for a cube doesn't necessarily give you a unique cube. Let's look at one of the cubes we had at the beginning. We said white, red, and blue were opposite each other, blue and white were opposite each other, and green and white were opposite each other. Let's look at the blue to red relationship. Well, because none of them are colored yet, we really could put the red on any of them and then rotate it so that the red goes in what we desire it to be. So I really want red to be on the front right. I don't know why I want that, but that's what I want. If I do that, then the blue will go on the back left. Again, had I put the red on the top, the blue would have to go on the bottom and I could rotate it to this position. Now I want you, we're going to color one of them blue and the opposite one white to represent the diagonal edge there. I want you to pick out which one you want the blue one to be, and then where will the white go? You can figure that out. All right, have you picked it? If you have, I claim that whatever you have chosen, I can describe how you can get there from any particular coloring. I'm going to choose to put the blue on the top and the white on the bottom. Maybe that's what you chose. If it's not what you chose, I can rotate the cube so that the red face moves 90 degrees clockwise, which will take the blue face to the back and the white face will come to the front. If I do another 90 degrees clockwise rotation of the red face, the blue goes on the bottom, the white goes on the top. If I do one more, the blue goes on the front left and the white goes on the back right. No matter what you picked, I covered it in that. So we can rotate the cube to get whatever we want. Now here's where things go south, if you will. Let's make a second copy here. There's my second copy. Now I have to do the white and green relationship. Well, it turns out that there are actually two different colorings. I could do white on the top and green on the bottom, or green on the top and white on the bottom. It turns out that these represent different cubes. If you look at the corner where the green, white, and red ones intersect, you'll see that the orientation of them is different. And I'm going to talk about dice to illustrate how this happens. Maybe you didn't know this, but when you look at a die, the opposite faces always add up to 7. So I can see the one side of the die, opposite that will be the 6. The 2 will be opposite the 5, the 3 will be opposite the 4. That's the way almost every die is created. Well, here's another one that's actually oriented a little bit differently. Same configuration, you'll always be able to find 1, 2, and 3 together. But this one is oriented a little bit differently. The first one, which is on the left side, I realize the silliness of that, but that's my right-handed die. I don't know who came up with that decision that it was going to be right-handed, but that means the other one is left-handed. Why is it right-handed? If you look at this corner where the 1, 2, and 3 meet and move from 1 to 2 to 3, you have to move in a counterclockwise fashion. On the other hand, on the left-handed die, you have to move to go from 1 to 2 to 3, you have to move clockwise. So that's the orientation that's different. You may have never known that, but that's something that's known as the chirality of a dice, or of a die. Chirality is something that comes up with sidedness, handedness. You learn about it in chemistry and other such things.